Okay, we're going to look today or introduce the idea of numerical integration. Actually, it's not something new. It's something we started with when we began to look at the area under an arbitrary curve. If you recall, we started by estimating the area with rectangles, right? We created what we call a partition. We subdivided the interval over which we're integrating, right? And then, for each of those little subdivisions, we approximated the area under the curve by a rectangle, the height of which was, left endpoint, right endpoint. But we could also use the midpoint. That's where we're going to start. And then we're going to improve upon that. Let's take a look at the following integral, the integral from 0 to 1 of e to the negative x squared divided by 2. This gives us the so-called, sort of like a bell curve or a Gaussian distribution here. And it's an important type of integral to be able to calculate in areas like probability and statistics, which are very important. The problem with trying to do the fundamental theorem of calculus part 1 on this integral is finding the antiderivative of e to the negative x squared divided by 2 is essentially impossible in terms of a finite combination of the functions we know. In other words, you can't find a function using our normal functions whose derivative is e to the negative x squared divided by 2. It's not e to the negative x squared divided by 2 because by the chain rule, you'd have a derivative of the inner function, which is going to be, negative 1/2 times 2x, right? The derivative of x squared is 2x. So negative x, you're going to have that negative x, and there's no negative x anywhere in this integral. So it would be impossible really to do, it turns out. So now later we will talk about infinite series, and we can represent the antiderivative of this function as an infinite series, but that's an infinite number of functions we're adding together. At any rate, let's talk about this. Integrating from 0 to 1, we're essentially finding the area under this curve here, right? And that's what we're trying to approximate. So how can we do that? Well, one way is with the midpoint rule. So let's look at an arbitrary function. We'll call that f here. And suppose we want to integrate over the interval from a to b. And so we are talking about finding the area, right? I could shade it in, but that area. So looking at the integral from a to b of this function. Okay, well, what we do is we subdivide the interval into n equally spaced subintervals. We're going to use equally spaced. And so, in this case, you can count how many subintervals I have. 1, 2, 3, 4, 5, 6, 7, 8. But for each one, to do the midpoint, what we're going to do, the height of our rectangle is going to be determined by the midpoint. If you remember, we've used the notation when we were talking about the left and right hand sum approximations. The x sub 0 was this a, this first endpoint, and then this right here was x sub 1, and then x sub 2, and so on, all the way down to x sub n minus 1, and b was x sub n. All right, so for each subinterval, so from x sub 0 to x sub 1, the first subinterval, what is going to be the height of the rectangle? Well, in the midpoint rule, what we use is the midpoint. All right, we actually did this with the left and right hand approximations. We used midpoint as well. So the height of our rectangle is going to be determined by the value of the function at this midpoint, which graphically would have a height equal to the y-coordinate of that point right there. And so that would be the height of our rectangle. Of course, the width is going to be the delta x. So let's talk about that, right? Remember, delta x, the width is still b minus a divided by whatever n is. Okay, so that would be the delta x would be the width of this interval. And so we would get our rectangle. And you can, if we zoomed in real close, you can see, you know, that rectangle is a little bit above the curve there, a little bit below the curve, but overall the area of this rectangle should approximate the area under the curve on this strip from x sub 0 to x sub 1. Okay, we're going to use c sub 1 for that midpoint. Okay, it's halfway between. So notice c sub 1 is, you know, halfway between. If I take x sub 0 plus x sub 1 and divide by 2, take the average, right? That's going to give me the midpoint. And then on the second interval, then we'll find between x sub 1 and x sub 2, we'll find c sub 2, right? So c sub 2 would be x sub 1 plus x sub 2 divided by 2. And then we would have the height, right, determined by that midpoint for our next rectangle. And so there would be our second rectangle, right? A little bit higher than the previous one, and so on. So we would continue all the way down until the very end. We would have the last midpoint would be the c sub n, right? That's the nth subinterval, and the height of that would be about right there. And so we would have a rectangle that would look like that. Okay. And notice c sub n, so going all the way down, c sub n would be x rather sub n minus 1 plus x sub n over 2. Okay, so basically you see the general formula for the c sub i's. They are equal to x sub I minus 1 plus x sub I over 2. That's the general formula. And so here is going to be the midpoint rule. It's just the sum of the areas of these rectangles, right? And the rectangles have a height of f of ci, all right? F of ci is the height of the ith rectangle times its width. The width is constant at delta x. So this is the area of the ith rectangle, right? I going from 1 to n. So if we sum this up, I equal 1 to n, then here is our midpoint rule, which we can use capital M for midpoint and a subscript n to indicate the number of subintervals. So more specifically, the way we'll see it typically, midpoint rule, all right? So approximating the value of the definite integral from a to b of the function f of x, right? And notice here, this delta x is constant for all of them. We can factor it out, delta x. And then it's just from I equal 1 to n, f of ci. So f of c1 plus f of c2, all the way down to f of cn. So this right here is the same thing as the summation I equal 1 to n of f of ci. Okay. Delta x again, bn minus a divided by n, and the c sub i's are found this way. Another way to think about it is it's the fixed value a, and then I minus 1/2 times delta x. In other words, go halfway. Typically, what we'll see is the distance between the midpoints is equal to delta x, right? In other words, the distance between C1 and C2 is delta x. C2 and C3 is also delta x. So what I typically do is just find C1 and then just keep adding delta x to find all the other midpoints. So let's take a look at a specific example here then. Just do this real quick using what we've just developed. So let's estimate the integral from 0 to 1 of e to the negative x squared divided by 2 with n equal to 5. So first of all, we calculate our delta x, which is just 1 minus 0, n is 5. So I get 1/5, which is, of course, 0.2. I'm going to leave it in a decimal form since we're going to approximate this using our calculator. And then so our x sub 0 is going to be 0. Our x sub 1 will be delta x added to 0, which of course is just 0.2. So I'm going to first get the x sub 0, x sub 1, x sub 2, and so on, and then I'll get the midpoints. Now I'll get the midpoints. So x sub 1 is 0.2, x sub 2 is 0.4, x sub 3 is 0.6. I'm just adding 0.2 every time. X sub 4 is 0.8. and x sub 5 is 1. And that's real important. With n equal 5, when we get to x sub 5, we stop, and we should be at the upper limit, right? If you're not at the upper limit, then something is incorrect. Okay. So what are the midpoints? Right? What is C sub 1? Well, C sub 1 would be halfway between x sub 0 and x sub 1, right? C sub 1 would be 0 plus 0.2 divided by 2. Well, that's obviously 0.1, right? So that's the halfway point between those two. And you can do the same thing for C sub 2 would be halfway between 0.2 and 0.4, right? Which would be what? 0.3, right? 0.2 plus 0.4 divided by 2 is 0.3. Or you can just note that these are all going to be delta x apart. So 0.1 plus 0.2 is 0.3. That gives me the same thing. C sub 3, halfway between x sub 2 and x sub 3, add 0.2 more is 0.5, right? And C sub 4 is 0.7, and C sub 5 is 0.9. So that's a way to get those midpoints. And therefore, I can find the m sub 5, the midpoint rule with n equal to 5. If you remember that, the delta x times f of C1, f of C2, all added together to f of C5 in this case. So I'm not going to use any summation notation either here. I'm just going to go ahead and do the delta x, which is 0.2, right? So there's the delta x, and then times f of 0.1 plus f of 0.2, sorry, 0.3, right? So that's C sub 1, that's C sub 2, and then C sub 3, C sub 4, and C sub 5. Okay. And now to do this, of course, what is this f of 0.1? If I plug it into the function, what is the function? Notice here's the function, right? So that's our f of x. It is e to the negative x squared divided by 2. Notice the negative is not being squared. It's not in parentheses, right? So it's negative x squared plus 2. So that exponent is always going to be negative. So it would be e to the negative 0.1 squared divided by 2. Now, all that would need to be in a parentheses in the calculator. And that's what I have here. I've already entered it in. And you can see I've got the 0.2, which is the delta x, times, and then parentheses. F of 0.1 is e to, in parentheses, negative 0.1 squared divided by 2. Notice the calculator will indeed do the exponent first. So it will square the 0.1 first, and then multiply by negative 1 and then divide by 2. So it's going to give you a negative exponent. If you put that negative 0.1 in parentheses and then square it, you're going to get an incorrect result because it will square the negative 1, making it a positive exponent. Okay. Then plus what 0.3 would be e to the negative 0.3 squared divided by 2, 0.5, right? E to the negative 0.5 squared divided by 2, and so on, 0.7 for f of 0.7 and then f of 0.9. Close the parentheses on everything, hit enter, and you get the value in this case is rounded off, right? 0.85668. Make sure, if you're asked to round your final result, say to 6 decimal places, that you remember the rounding rule. So I go all the way to 6 decimal places, I see a 7. The next decimal place is a 6. Since it's 5 or higher, I round this up to 8. So there's rounding it off. Notice I don't round off though till the end. Don't do each one of these individual calculations separately, rounding off, and then add them all together. Get used to doing it all in one step in the calculator like I've done here. Okay, all in one step in the calculator. And this is 9 times out of 10. A lot of times where the problem comes in, everything's set up fine, and then you do a little incorrect entry. So on the test or on homework, you need to show exactly all the things that I've shown here, right? Your midpoints, how they were calculated, and then plug into the formula the values that you have. Okay, plug those in and then do that. Because if I don't see the values plugged in, I don't know what what you're doing, at least. Now, calculator value, that will be important, right? That you're able to use your calculator to get that actual value calculated. Okay, midpoint rule. Can we improve on the midpoint rule? We talked about left endpoints, right endpoints. Is there a way to improve? So this section really is about two methods. More important, midpoint rule is part of it, but the trapezoid rule and Simpson's rule. So we're going to look at trapezoid rule first. And the trapezoid rule, as the name implies, is based upon using a trapezoid. And what is a trapezoid? I hope some of you remember that from basic geometry. It's a quadrilateral. And I'm going to draw one over here. Two sides are parallel. Okay, two sides are parallel. Okay, so here's an example of trapezoid. Now, oops. So you know, a rectangle would be a trapezoid technically because it has, well, it has two sides parallel and the other two sides parallel, but the minimum is two sides parallel. So a rectangle technically is a trapezoid. But in general, the two sides don't have to be parallel. These two sides have to be parallel. And typically the dimensions we have, I'm going to call this H, and I'm going to call this longer length capital B and this smaller length little b. Now, what is the area of a trapezoid? What is the area? We know an area of a rectangle is base times height, right? But here we got a, you know, I guess a height, we can do it that way as height. And we got two bases, right? A big base and a little base. How's that work? So some of you probably know the answer. And if you don't know the formula for it, here's a little hint. If I do a little dashed line connecting the opposite vertices here, notice that I've divided the trapezoid into two regions, each of which are what? A triangle. And we know the area of a triangle is 1/2 base times height. So the area of this little one is 1/2 base times height, little b times h. And the area of this one up here is 1/2 big base b times height h, right? And factoring out, a lot of times it's written this way, you can factor out the 1/2 and the h, and you get this formula. That's the formula for the area of a trapezoid with the dimensions as indicated on the diagram. So how does the trapezoid rule work? Well, again, suppose we're integrating this function f of x, and we're going to integrate it from a to b, okay, a to b. So what we're going to do is we're going to again partition the axis into n equally spaced subintervals. I'm just going to draw 4 in this case. So again, this is x of 0, this is x of 1, this is x of 2, and so on, dot, dot, dot. And then we get to x of n minus 1 and x of n. Okay, in my case, you know, x of 3 and x of 4. But in general, I don't know, you know, you might have 5 subintervals or 10 subintervals or whatever. Okay, so the idea though is for this first region, this little subinterval between x of 0 and x of 1, what we're going to do is we're going to find the height at the left end point, which is f of x of 0, and the height at the right end point, which is f of x of 1, all right? And we're just going to, instead of doing a rectangle, I'm going to connect with a line these two, right? And you can see I've got a trapezoid here for this whole shape, right? This whole shape is a trapezoid. And I'm going to approximate the area under the curve by the trapezoid. You see that? And so the second subinterval from x of 1 to x of 2, I'm going to right, draw that, and so on, all the way to the last, the nth subinterval. We are going to approximate the area under the curve, again, by a trapezoid. Okay. So the area of those trapezoids added up will be the approximation that we call the trapezoid rule. Now, notation that we use here is y sub 0 is going to be f of x sub 0, and y sub 1 is going to be f of x sub 1, and so on, all the way down to y sub n is f of x sub n. Okay, and what we're going to do is we're going to use this now to find out what is the trapezoid rule, capital T, with n subintervals. What does it equal? Okay, so let's find the area of the first one. Well, it's a trapezoid, and we've got the formula over here. So it's 1/2, and we got little b and big B. Well, the little b is this, right? This side length in this case. Here's our little b, this side length, and our big B is this side length, right? So little b is just the height of the function at x sub 0. So it's f of x sub 0 or y sub 0. Plus big B is the height of the function at x sub 1. That's f of x sub 1, which we're calling y sub 1. So this length is y sub 0, this length is y sub 1. And then what's the width here? Well, for all our rectangles, remember they're the same thing. It's delta x. And that delta x is the same delta x we had before, right? Delta x is still equal to b minus a divided by n. So that's a fixed value. So that's the first. So that's the first trapezoid. Second trapezoid will be 1/2 what? Now we got this length here, which is y1, plus this length here, which is y2, times delta x. Again, the width, the h value we're calling here is the same. Okay, and we just continue going through all of them until we get to the last one here, which will be what? 1/2. This is y sub n minus 1, right? Which is this height, plus y sub n times delta x. Okay, so first of all, notice for each one we have a 1/2 factor and a delta x factor. I'm going to factor out the delta x over 2. And what's that leave? Well, here I got y sub 0, but here I got y sub 1, but I also have a y sub 1 here, right? So when I factor out, right, the delta x and the 1/2, I'll have y sub 0 plus y sub 1 plus y sub 1. That's 2y sub 1. And I'll have a y sub 2, and then this third, right, trapezoid over here would have y sub 2 plus y sub 3. So I'll have y sub 2 plus y sub 2. I'll have 2 y sub 2s. And so on. That will continue until I get to what? There'll be 2 y sub n minus 1s, because this y sub n minus 1 will be in the nth trapezoid here that we used, but the previous one, the n minus 1 trapezoid over here. Okay, and then plus, well, there's only one y sub n because it's the end. It's only used in one trapezoid. Okay, and that is the formula for the trapezoid rule, right? So to summarize down here, trapezoid rule, right, for the integral from a to b of f of x dx is delta x over 2 plus y sub 0 plus 2y sub 1, 2y sub 2, 2y sub n minus 1 plus y sub n. Notice the coefficient pattern of 1, 2, 2, 2, 2, 2, 2, 2, and then 1. That's important in these numerical methods. There's typically a coefficient pattern that you can use to help you remember how the formula is done. Okay, now on the tests and things, I'm not going to require you to memorize this formula. I will give it to you, but it's not too bad to remember this one. Okay, again, it goes through the definitions of all the things that we've talked about in this. So in the next video, we will look at an example of applying trapezoid rule and see how that works.